Okay, Year 12, so I'm going to get you to fly solo on this next part of the notes. So grab them and pick it up where we left off on Wednesday. So what we're going to do is continue solving logs. So here's another one to solve. Now, if we're solving for x, it might be a good thing to just sort of know what the acceptable values of x are going to be. So this one here, it's going to be for values of x larger than 0. Now for this one here, it's going to be for values of x, or let's just say that 9x take 2 has to be larger than 0, 9x has to be larger than 2, x has to be larger than 2 on 9. So basically this one here is the constraint. So when we get solutions to this, what we're going to make sure is that the solutions we get, the values of x that we get, have to be larger than 0. Right, so let's go for it. So what we'll do first of all is this 2 here, we're going to bring it back up to there. So it's going to be log e x squared plus log e 4 equals, why did I write a 9? Log e 9x take 2. Alright, so once we've done this move here, then we're allowed to do the combine law. So what we're allowed to do is stick these two logs together once we've got no coefficient. We can't make this move when there's this coefficient here. Alrighty, so what we're going to do is rewrite this as one log, which is log e 4x squared equals log e 9x take 2. Alright, so now what we're going to do is use that same sort of equate the base type technique, that if this is the same as this, that means this is the same as this. So we can grab 4x squared and we can say that that must be the same as 9x take 2. Now remember, these do not cancel out, so don't write a cancellation there. Okay, they're still there. We're just saying that if that is the same as that, then that must be the same as that. So we're just going to take this part out because that allows us to solve for x. Alrighty, what we'll do is go 4x squared, take away 9x plus 2 equals 0. Now invariably this will be an easy non-monic solve. Maybe. I think that's 4x and that's going to be x. And they're both going to be negative. Yes, there we go. So we're going to get 4x take 1. X take 2 equals 0, x equals a quarter, and x equals 2. Okay, so we've got two solutions and both of them are greater than 0, therefore both of them are acceptable. Okay, and this one here, so let's have a look. Alright, so I think the first move we'll make is combine these two together by the addition log law. So we'll go log e, and what happens for common based logs is we multiply these two together. So I'm going to go log e 2 3x plus 5 equals 2. Now I'm going to say log e 6x plus 10 equals 2. Alright, now how am I going to solve for this? Well, what I'll do is take this out of log form and put it into exponential form. So the base is the base, e to the 2 equals 6x plus 10, e to the 2 take 10 over 6 equals x, and it's solved for x. So we're done. Alright, so I think I said 1 to 7 the other day. Now finish them off 8 to 12. Alright, let's get into graphing log functions. So we've seen already that this graph here is e to the x and this graph here is log e to the x. They're inverses of each other. And here's the graph of log 2x, log ex, and log 3x. So you can see they're fairly similar. All of them have this same x-intercept. They're just, I suppose you could consider dilations of the e to the x function, which we'll explore later on. Alright, so let's just quickly go through how they work. So f of x equals log ax. What they want us to do first of all is do f of a. So that is log a, and that, as we've found, is 1. Okay, so when I put a into it, okay, the answer is going to be 1. Right, what about f of 1? That's going to be log a 1. A raised to what power gives me 1 as a result? The answer is 0. Okay, so here's that. When x is equal to 1, y is equal to 0. And finally, we've got log a 1 on a, which is equal to log a to the negative 1, write it with a negative index, grab that, shove it out the front, negative log a, which is negative 1. And there it is here with base e. Okay, so this would be assuming that we're using log base e here. All right, so the maximal domain and range. So the domain of f is what? It's going to be 0 to positive infinity. Okay, so they're all the acceptable values, or all the loggable values, I suppose, if you want to call it. And we already know that. We've got to log, we can only log numbers greater than 0. And the range of f is going to be all real numbers. Okay, can produce anything. Okay, and remember, these are just the reverse of the exponential function. What is the equation of the asymptote for f of x? Well, all it's going to be is, instead of being y equals 0 for the exponential function, since it's the inverse, it's going to be x equals 0 for the log function. Okay, strictly increasing over the domain. If the log value is greater than 1 over the domain, ooh, this is interesting here. Okay, so when our log base is greater than 1, we're going to get this happening. Okay, and so we're going to say it's strictly increasing over the domain of x is an element from 0 to positive infinity. So it just keeps increasing, basically. All right, now here's an interesting one. When the base is between 0 and 1, i.e. It is this kind of value, or this kind of value, 1 on a, then what's going to happen is, no, that's not actually this case. This is when we've got a log base between 0 and 1. And actually what I'll show you later on is this is going to be the same as a reflection in the x-axis. All right, so what that's going to do is produce this kind of graph. Okay, and what that's going to mean is it's going to be strictly decreasing over the domain x as an element 0 to positive infinity. So you're just going to have to trust me on that one just for the moment, when we've got a base that is between 0 and 1. This actually rarely happens. Okay, generally speaking, we use bases e or 10. Okay, so this one here is going to be quite a rare thing to actually happen in the first place. All right, so let's sketch one of these log functions. Okay, so the way I like to do these is we basically are going to ignore the vertical translation, not worry about it. What we're going to do is find out the smallest loggable value. And again, I don't know whether that's a word, loggable, but that's the way I think about it. So we're going to say that 2x plus 1 has to be larger than 0. Okay, that means 2x greater than negative 1, x has to be greater than negative 1/2. That's actually where our asymptote is going to be. So this is the standard log function, which looks like this, with an asymptote there. And what it's doing is shifting a 1/2 a unit to the left. So let's pop that in. So that's going to be x equals negative 1/2. Alrighty, now what we'll do is, shall we get the, let's get the y-intercept. So y-intercept occurs when x is equal to 0, so that's y equals log 2. 0 goes in, that's 1 plus 2. Okay, 2 raised to what power will give me 1 as an answer? That's got to be 0, so it's 0 plus 2 equals 2. So it's going to be there. And we're going to get an x-intercept somewhere over here. Okay, so x-intercept occurs when y is equal to 0. So we're going to go negative 2 equals log 2 2x plus 1. So what I've done is set y to 0 and then subtract 2 from both sides. Okay, The next move is to switch to to exponential form. So 2 to the negative 2 equals 2x plus 1. Now 2 to the negative 2 is 1 over 2 to the 2 equals 2x plus 1. That's going to be, running out of room here, a quarter take away 4 over 4 equals 2x. So I've subtracted 1 from both sides. That's going to be negative 3/4 equals 2x. Divide by 2. When we divide this, it's the same as multiplying by a half. Negative 3/8 equals x. Okay, so here is negative a half, which is 4/8. So 3/8. So negative a half is negative 4/8. So if you imagine this cut into 8 parts, it's going to be quite close to it. Okay, so I don't know whether that measures up exactly, but it's good enough. And we can see here what our log's going to do is go through these two values here. So let's send it through. Okay, that's probably okay. Alright, so key features time. So we're going to go when x is negative 3/8, the y value is 0, and when the y value is, or the x value is 0 rather, the y value is 2. Alrighty, labelling the asymptote with its equation, x-axis intercept and y-axis intercept with coordinates, state the implied domain and range. Okay, so the dom of f is going to be the smallest loggable value, which is negative a half, but you can't log it, to positive infinity, and the range of the function is going to be all real numbers. Before we sketch, state the transformations. Well, I did consider the transformations, I suppose. We're not worried about this one when we're drawing log graphs. All we're worried about is the horizontal translation, because that sets up the asymptote, and once we know the shape, yeah, it's pretty much sorted from there. Alrighty, change of base. Okay, so changing the base of an algorithm is a little old-fashioned, and most of you guys won't really have to do it, but us oldies did have to do it. So it was needed before the advent of cheap calculators and computers. And this picture here is of the calculator I used in year 12. And if you look at these older calculators, or you pick up your one from year 7, the green calculator, you'll notice that when you do logs, you can only log in base E or base 10. Okay, so if I wanted to find out what log 5/100 was on the calculator when I was younger, I couldn't do it by doing log 5/100. I'll show you on Mathematica. So let's just do it on Mathematica. So I'm going to go log and 5/100, and let's get an approximation, and it just does it straight away. Although interestingly, Mathematica has changed the base for us as well, or shown us the exact answer. But yeah, there's our answer, or our approximation anyway, 2.86. Now, if I didn't have the ability to type this in on this calculator, how would I have done it? Okay, so what I'll do is just talk you through how change of base works. Okay, and it serves a couple of purposes. We can see how graphs are dilated from whatever axes we look at, and there are, or is, a question that comes up every now and then that does require an understanding of change of base. Okay, so what we're going to see here is how it's done. Okay, and there is a rule for it. It's not on your formula sheet. Okay, but yeah, I'll show you how it works. So if we've got log A, B equals C, then what we can do is switch to exponential form, okay, which is A to the power of C equals B. All right, and then what I can do is take any log, the natural log, or really any log I like of both sides. Okay, so I've taken log X of both sides, where X is whatever base you want. All right, now we know that there's this move where I can grab that C and shove it out the front. So that's what I've done in this line here. And then all we do is we divide both sides by that. So C equals log XB over log XA. All right, now going back to the beginning, I've got log AB equals C, and all I'm doing here is replacing C with this new version. So log AB is just the same as C, which is this. So log AB equals log XB over log XA. Alright, so there's the change of base formula. Let's use it on this particular problem here. So if I have log 5 100 and I don't have the ability to work this out because my calculator does base E or base 10 only, what I'm going to do is change this into base E for argument's sake. So we're going to go log, now I choose whichever base I want, that's E that I want to use, and our B value, now this B value is this one here, so that's 100, over log E, and this is our A value is this one here, which is 5. Alright, so there it is there. Alright, so this particular answer, so if I do this, and I'll show you on Mathematica, I'll do it right now. So what I would do is I'm going to go log, and to use base E, you put a capital E in, 100 over log E 5. And we'll get the numerical value, and of course it's exactly the same. Okay, so again, we would have had to, we couldn't work this out back in the day. Okay, so what we had to do with log base 5 is just turn it into a log base E, or the other alternative was log base 10. And our calculators did base 10 as well. Okay, so what I want to show you now is the base switch law. Okay, so I've kind of forgotten how this works, but I'm just going to have a bit of a play here. So what I'm going to do is take log A, B, and I'm going to say that that equals C again. Okay. Now what I'm going to do is switch to exponential form. So I'm basically using the change of base rule. So I'm going to go A to the C equals B. And now what I'm going to do is take a log of both sides. Now the log I'm going to take of both sides, what's going to happen to make this look like this is that I'm going to have to cancel out this side here, or it needs to become 1. So can you think of what log base I'm going to take to both sides? If you thought he's going to take the log base B, that's correct. So what I'm going to do is log B A to the C equals log B B. Alright, now that C goes out the front to give us C log B A, and this becomes 1. Now what I'm going to do is C equals 1 over log B A, and hence if that's C, that is that, which means log A B is the same as 1 over log B A. Alright, that's called the base switch rule. Alright, so need to know that one, and I'll show you where it comes up a bit later on. So using change of base, a log of any base can be quickly transformed into a log of a different base. Okay, so what you can do is if your log function is in base 2, you can change it to log base E, and you can do the same to the exponential function. And why do it? Well, it allows the function to be more easily differentiated by hand, and also appeases, as I've said, old school mathematicians who will say that the only two bases really are base E or base 10. Alright, so what we can do then is we want to state a transformation that takes this to this. Okay, so we want to go from y equals log 5x to log y equals log ex. Alright, so what's the move that we would make? So essentially, yeah, I want to turn that, or I want to get that to look like this. So what do I do to this to get it to look like that? Okay. All right, so the way we're going to do it is we're going to run the change of base on this thing here. So it's going to be rewritten as log y equals, all right, and what we're going to do is choose base e as our change of base. So we're going to go log e. Now, if you recall, and you might need to flick back a couple of pages, what we do is we grab this one here, and that's going to go there, log e x over log e 5. And we're going from that to that. All right, so what I'm going to do now is rewrite this as y equals 1 over log e5 multiplied by log e x to that. All right, so now we've got log 5x, and we've just rewritten it as this. All right, now why did we do that? Well, it's really easy now to go from this to this. So how would I get this to look like this? Well, all I would do is I would multiply this function here. Okay, all I would do is multiply. So if this was f of x equals 1 over log e5 times log ex, all I would do is just multiply f of x by, so I would do log e5 multiplied by f of x to create my new function. Now, why that? Well, all that does is when I multiply this function here by that will cancel out, leaving us with log ex. Okay. Now you can see that this here is a transformation. It's a dilation factor log e5 from the x-axis. So we're going to say dilation factor log e5 from x-axis. Okay, so let's do this one now. Okay, so this time around what we want to do is turn 5 to the x into e to the x. Alright, now this one here, what we're going to do is rewrite this as base 5. Okay, now you might be kind of wondering, no, it's currently written as base 5. We're going to write it as base e. So to convert that into that, it just is going to be helpful if this has got a base e. So there's a pretty simple move. All we're going to do is rewrite this as y equals e log e 5 to the x to y equals e to the x. Alright, now this has got a base e, okay, and what we're going to do is just shuffle this around a little bit. I'm going to rewrite this as e, x comes to the front, so we've got that coming to the front, so it's x log e5 to this, and then because these two are just multiplying, I can just change the order. Y equals e log e5 x to this function here. Alright, so remember this law here, log e, they basically just undo each other, which is just the same as y equals 5 to the x. Okay, so I've basically kind of, if you want, unsimplified it to allow this all to happen. Alright, now why did I do this? Well, what you can see is this function here, to get it to look like this, I'm just going to have to undo this dilation from the y-axis. So this thing here, okay, I need to undo that. Alright, so if you want to imagine this is a function, f of x equals e log e 5x, and you want to create g of x, which is this function here, e to the x, you think to yourself, okay, well, what do I do to f of x to make this happen? Okay, what would I sub in? And what would I do? I would say that g of x equals f of, and what I would do is replace x with x over log e5. Okay, so what this represents here is when this will go in, these two will cancel out. Actually, I'll show you. Let's try it out. So I'm going to create g of x, which is f of this. So I'm going to go e, and where I see x, I'm going to replace it with this. So it's log e5 times x over log e5. Now those two cancel out, leaving us with g of x equals e to the x, which is what I want to turn it into. Alright, so this is our transformation. How would you describe this? Well, all that's going to be, so what I would do is put in to f, or I drop into the function this. That's going to be 1 over that, which represents a transformation that is a dilation factor log e5 from the y-axis. Okay, so remember that dilation from the y-axis, what you would do is drop in 1 over that, or x over that, to make that happen. Okay, all right, and I think the last one, maybe? No, second last one. Third last one. Bit to do here. All right, is this one here. So find a transformation that takes this to this. All right, so same idea again. What we're going to do is just change the base of that. So I'm going to rewrite that as y equals, instead of base 3, I want to make it base 2, because I want to turn this into this. So I'm going to use the change of base rule, which is log 2, and we write down x over log 2, 3. All right, now what that means is this is the same as y equals 1 over log 2, 3 times log 2x, and that's what we want to do. So basically, to turn this function into this function, which is this function into this function, all I have to do is undo that. Okay, and all I would do is this function here would be multiplied by log 2, 3. Okay, so I'd say it is a dilation factor log 2, 3 from x. And again, what you could do is just try that out with function notation. So let's let this, so we'll call this f of x equals 1 over log 2, 3 times log 2x, and let's do this dilation factor 2, 3 from x. So g of x equals f of, no, log 2, 3 f of x, which basically says that function f of x multiplied by log 2, 3. So that's going to be log 2, 3 times 1 over log 2, 3 times log 2x. Those cancel out, leaving us with log 2x, which is what I wanted. There it is there. Okay, find a transformation that takes this to this. Okay, so what we want is, instead of base 3, we want this to base 4. So we're going to go and write this down as y equals 4 log of 4, 3 to the x, and we want to go to y equals log, not log, 4 to the x. Alright, so same as last time, what we're going to do is grab that x and shove that there, and then I'm just going to change the order so that x is second. Y equals 4 log 4 3x to this. Alright, and you can see, to make this, or turn this into this, what I'd have to do is sub in x over this amount here. Okay, so again, let's call this y function, this one here, f of x equals 4 log 4 3x, and I want to create this function here, g of x. What do I need to do to f of x? I think I need to sub in x over log 4 3. Okay, and what will happen is that goes in there, these will cancel out, leaving us with log 4x. So this is the transformation that makes it happen. So if I'm dropping f of x on this, then my transformation is going to be a dilation factor log 4 3 from the y-axis. All right. Okay, the expression that equals which one of those? All right, so you might recall the base switch rule. Okay, so the base switch rule says that this log CA is the same as 1 over log AC. All right, and so there it is. It's got to be B. So 1 over, and they should switch, and 1 over, and they should switch. That question there came up in 2011, exam 2, it was question 22. Then in 2020 or 2019, this more or less the exact same question came up. And luckily this question here hung around in my notes until that year, and my class got something staggeringly high in it. It was like 40% above the state. So I suppose just because you haven't seen it come up for a long time doesn't mean they're not going to whack it on this year. So I'll leave that question in maybe for another 10 years and it might come up again. Anyway, there's your exercise today. It's 5E. All right, noting that 6 and 7 are the tougher questions here. They're the dilations questions that we've just been doing. So good luck with that.